differential equations. We're on 4.4, the second day. And again, what are we doing? We're solving non-homogeneous differential equations. Most of these are second order. Of course, we can venture off into other powers too. But as you look at the right-hand side, you notice it's not 0. You can very quickly say, oh, I see an 8e to the x. It does seem reasonable that our particular solution would be a times e to the x. However, what you must do, and this is super, super, super important, is you have to solve as if this was equal to 0. You've got to take a look at the y double prime minus 5y prime plus 4y equals 0. And if that were the case, we were doing that quite a bit, you'd quickly come up with this quadratic when you would substitute in a general solution of y equals e to the mx. This factors into m minus 4 and m minus 1, and it will not take you long to come up with m equals 4 and m equals 1, meaning that a general solution would be c sub 1 e to the 4x plus c sub 2 e to the x. So you always must start here. We're always going to do that. We're going to have this as part of our final answer. We're always going to have this homogeneous part, but this is what I'm getting at. Once you do that, you can see, hey, wait a minute, this is like a repeat solution for the particular. So we're going to assume for our particular, not that we have a e to the x, but because we've already got something with an e to the x, we'll treat this as if it were a duplicate. We'll have ax e to the x. Let's real quickly take a derivative via the product rule. The derivative of e to the x, of course, is e to the x. The derivative of ax is just an a. Then we'll take a second derivative. By the way, right now this should look very familiar. You'd say, wait a minute, that ax e to the x, that seems like we just did that. We literally just did. So as we take this derivative of that ax e to the x, we get the answer that we had for y prime. Now you could do the product rule again. It's rather silly to. And then you take your derivative of a e to the x. You just get that. So combining our like terms, we've got an a e to the x and another a e to the x. That's a 2a e to the x. Now what? Well, we're going to go to our differential equation with this 8e to the x on the right hand side, and we're going to substitute in what we're seeing here. Here's an ax e to the x plus 2a e to the x minus a 5. Well, y prime's right here. We'll have an ax e to the x plus a e to the x. Then we'll say plus a 4. Well, we'll have an ax e to the x. And then our right-hand side, we just have an 8 e to the x. So let's just go ahead and do some combining of some terms here, distribute wherever we can. Here we'll have a 2a e to the x. When we distribute this negative, we'll have a negative 5ax e to the x minus a 5a e to the x. Here we have a plus 4ax e to the x equals an 8e to the x. Well, one thing I hope you can notice rather quickly is you do have some terms with an x e to the x here. You can see that we've got several of them. Out in front I have a 1ax e to the x. Here at the end I have a 4ax e to the x. That is up to a positive 5ax e to the x, which cancels this negative 5 here. All of these terms are gone. And that leaves us with a 2a e to the x minus 5a e to the x, which quickly we can see is a minus 3a e to the x. And hey, look at that. We can do more or less just a coefficient analysis, or we can divide both sides by e to the x regardless. You know what? We're really saying that a would have to be a negative 8/3. And right now, what we can do is go back and say, look, our solution that we had, of course, is that general. You can see it at the top of the screen here. The general homogeneous solution. We're always going to have that. But then our particular, we had an ax e to the x. Well, our a is a negative 8/3 x e to the x. We assumed that we had some form like that. So that's really what we do to get a general, a final solution. We've got our homogeneous solution and our particular. We put them together, and that's our final answer. So what we're about to do right now is maybe look at an extreme case. Say you had a really obnoxious problem like what you see here. The right-hand side, dare I say, might appear to be terrifying. Because, my goodness, look at this. You can see, oh, wow, I've got this 4x minus 5 right here. You think, holy cow. And then I'm going to have a 6x e to the 2x and x squared plus 2 cosine of 3x. Of course, first you solve your homogeneous solution. It's as if it was equal to 0. But for your particular, look in yellow. If you had 4x minus 5, think of that as an ax plus b. Look right here. You've got a 6x e to the 2x. Well, 6x is linear. It's like something with a multiplied to x plus a constant. Here it's kind of like 6x plus 0. That's a very general term. Look at our last component right here, this x squared plus 2 cosine of 3x. This really gets complicated. They're multiplied together right here. The x squared plus 2 is quadratic, isn't it? So you'd have a general quadratic, ex squared plus fx plus g. But remember, when we have a trig function, we'd like to also consider, as we're dealing with these derivatives, or these differential equations, that a cosine of 3x could be tied to a more general form of something with sine of 3x added to it. So one way you could proceed is to take the derivatives, a first derivative and a second derivative of this whole frightful mess right here. It would work, and you could solve a system as you plug those in and try to solve for A, B, C, D, E, F, G, H, I. Here's maybe the better way, the preferable way. Or you can break it up into parts and solve one by one. What are we really getting at? Well, we're saying this. Let's just say that we had in yellow. We could say y sub p sub 1 have an ax plus b, and then you take your derivative, and that would just be an a. A second derivative would be 0. Just worry about that component and solve for a and b. Do that separately. Then you get the idea. Then you move on to the other parts. It's way more accessible this way, and for sure that's a preferred way to go. Now, we do have another example coming up, and we're not going to be able to finish it, I do not believe, but it does jump into the other side of it, solving an initial value problem. And you can see we've got a second order linear differential equation, but it's not homogeneous. It's non-homogeneous. We have something other than 0 on the right. But tell you what, we're going to, first of all, just a friendly reminder, sometimes kids miss this little point right here. There is a y prime component. It's just a 0 out there, right? And, as you'd assume that you have a homogeneous differential equation right now, pretend that the right-hand side is 0. And again, this is coming from that assumption that we'd have e to the mx and, take derivatives and substitute it in. Very quickly, you'd see that m squared plus 4 equals 0. M squared would equal negative 4. You'd take your square roots and you'd get m equals plus or minus 2i. There'd be a 0 out in front. So your alpha would be 0 and your beta would equal 2. Now, in general, what we have been seeing is it's e to the alpha x. Then we'd have a constant cosine of beta x plus another constant sine of beta x. And of course, right now, we know that alpha would equal 0. That's 0 times x. That's going to disappear. So what you're going to have is just c1 cosine of 2x plus c2 sine of 2x. And that's a fantastic start. It's a wonderful start that we're going to need down the road. But of course, this is not where we just stop. We have this right-hand side equals negative 2, and that does beg the question, what should we let our particular solution form be? Well, if you have a constant on the right side, let's assume that, a particular solution is in fact a constant itself. Y prime would be 0, y double prime would be 0. And hey, this is really nice to plug in. As you do that very fast, you just get a 0 plus 4a equals negative 2. A would be negative 2 over 4, so a is negative 1/2. And that's your particular solution, in fact. So, we're going to take our homogeneous general solution and our particular, and we're going to say, hey, you know what? Very nicely done. We can write our final answer right here if it didn't have initial values. If we didn't have additional parts to find, we'd be done. However, there is some more work to do. Look at this. We're going to try to find these constants. We've got y of pi over 8 equals 1/2. That means let y equal 1/2 when x is pi over 8. And let's go ahead and see what happens. We'll have 1/2 right here. Cosine of 2 times pi over 8, that's going to be pi over 4, isn't it? And the same thing over here. This is 2 times pi over 8. And, if we've got pi over 4, the cosine of pi over 4, we all know is root 2 over 2. So that's a root 2 over 2 right here. Another root 2 over 2 right here. And tell you what, I see a whole bunch of halves. How about we just help ourselves out and multiply everything by a 2? You can certainly do that. It's going to really clean some things up in a hurry. These 2's are going to be gone. And these are gone also. So without too much work, you add this 1 over here, and you'll have 2 equals radical 2 c1 plus radical 2 c2. So we're not done. We're also going to have to take a derivative and use the other initial condition. You can see we also were told about y prime. Now, just looking at the time here, sadly, I think we're going to run out. So we're going to stop right here and pick up with the conclusion of this problem on our next video.